Modeling the propulsion of magnetic levitation trains. For my initial trials, I planned to model the phenomenon that is the train levitating. I tried doing this using circular magnets, but I soon found out that the magnetic poles in circular magnets are not aligned how I first thought. I believed one side of the magnet would be the exact opposite pole as the other side. Turns out, each side of the magnet has both a north and a south pole. This caused my train to derail, and it would not levitate. For my second trial, I thought it might help if I switched my magnet type, so I chose to use magnetic strips. One side of the magnetic strip was sticky and the other side was non-sticky. After sticking these strips to my railway and my train, I found out that the non-sticky sides of the magnetic tapes were of opposite poles and attracted to each other, so my train was attracted to the track and most definitely did not levitate. So for trial 3, after not being able to find magnets that could accomplish what I needed them to, I switched my experiment to model how maglev trains are propelled forward. Initially, I used 20 gauge bare copper wire. This gauge was not thick enough, would not stay coiled, and due to its thin nature, I believe it was not strong enough of a conductor. The battery train would not travel through. Trial 4 was a success. Using 18 gauge bare copper wire, neodymium magnets, and AAA battery, I was able to model the propulsion of maglev trains. And here's a video of this happening. So the magnets on either end of the battery make contact with the bare copper coil, and when they do this, electricity is created, and electrons flow through the coil. When electricity runs through a coil, it will create a magnetic field. In this way, my artifact models electromagnets that are used in maglev trains. The magnetic field is created is non-uniform, and the strongest push from the field is felt in the middle of the battery due to the orientation of the magnets. You can see this in the figure. If the push is in the right direction, the battery will travel through the copper coil. So for some definitions, electromagnets are a type of magnet in which the magnetic field is created by an electric current. Usually these magnets consist of a wire wound into a coil, and a current will flow through this wire, creating a magnetic field. Superconducting magnets are an electromagnet made from coils of superconducting wire. My artifact was able to model the phenomenon of electromagnets on a tiny scale. Maglev trains use superconducting magnets. And these superconducting magnets must be cooled to very low temperatures during use, somewhere around less than 450 degrees below Fahrenheit. These provide magnetic fields of greater strength than normal electromagnets. They also require the use of superconducting wires, something a little better than my 18 gauge bare copper wire. So my source and inspiration came from a really cool YouTube video by Physics Girl, titled "The World's Easiest DIY Electric Train."